Swayam Prabha. Digital India. Educated India.
Okay, so we'll talk about Knapsack crypto system, Markley-Hellman Knapsack crypto system. So this is a public key crypto system. So basically it is coming from the what is called knapsack problem. So problem is, suppose you are going to the market to buy some apple. So your parent asks to buy, say 100 kg apple. So say 100 grams apple, say, or 950 grams apples. Okay, and you see in the market, so there are apples whose weight are say 1150 grams, 170 grams, like this, 250 grams. So 520 grams and say 370 grams, like this. So these are the apples. So this we denote by A1, A2, A3, A4, A5, and so on. Okay. So your target is to buy 950 gram apple total exactly. So that means you have to choose. So this is a collection of apples. A1, A2, say there are say 100 apples, A100. So this is the collection of apples, A1, A2, A100. Among this collection, you need to find a subset. This is also called subset sum problem. You need to find a subset such that whose sum is this 950. So this is the all collection. Among this, you need to find a subset, which is basically, say S could be say AI1, so there are k apples such that summation of AI1 plus AI2 AIK is 950. So that is the problem. So problem is, we have given some integer. So this is also called subset sum problem. We have and this set is called a knapsack. This subset is called knapsack. So we keep this apple into our bag. So that bag is called knapsack. So we can formally write this problem. This is called subset sum problem. No computer, please. Okay, so we call this subset sum problem. Okay, so problem is, we have given some integer A1, A2, AN. So these are input, and we have another integer which is S, which is called target, which is also another integer. And now we have to find out a subset. The output will be, so we have to find out a 0 1 vector x, say x1, x2, xn, such that all xi's are all xi's are 0 or 1, such that summation of a1 x1, so x1 a1 plus x2 a2 xn an, this is S. So that means if my subset is say A2, A3, A5, if this is our subset which is sum is giving us S, then the corresponding x2 is 1, x3 is 1 and x5 is 1 and remaining are 0. So, that is the collection. So, this is called knapsack, this is knapsack. So, we have to find out this 0 1 vector, this is the 0 1 vector basically, this will give us a subset. Okay. So, in general how many subsets are there? There are 2 to the, this is the power set number of subsets. So, 2 to the power n. So, in general we have to, the exhaustive search is we have to try for all subsets and we check whether this is matching or not. So, in general we can try for all xi. So, each xi is 0 or 1. So, that is 2 to the exponential time algorithm which is hard. So, in general, so this is the problem, this is called subset sum problem. So, this is this original version is the decision problem. Is there exist a yes or no, that is called decision problem. So, decision problem in itself is hard, not only it is a NP hard problem, and so this problem is computationally infeasible problem, it is hard problem. Now, how we can make it a feasible, computationally feasible problem? If we take this input in a super increasing way, if our AIs are super increasing sequence, then this problem is maybe feasible. So, that we will talk about. So, yeah, so if these AIs are super increasing sequence, A through N is a super increasing. What do you mean by super increasing? Super increasing sequence. Super increasing means A2 must be greater than A1, A3 must be greater than A1 plus A2, A4 must be greater than A1 plus A2 plus A3, this way. So, AJ must be greater than A1 plus A2 dot 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 AJ minus 1. So, AN must be greater than A1 A2 AN minus 1. So, if you take any point, any integer, is must be bigger than sum of 2 previous integer. So, that is called super increasing property. So, if our AIs are super increasing sequence, then this subset sum problem having a polynomial time algorithm to get the that vector. So, what is that algorithm? So, let us write that algorithm where we are taking a super increasing sequence and we have a target S and we need to get the subset whose sum is basically S. Okay, so, this is the algorithm to finding the algorithm. Okay, so, input is the super increasing sequence A1 A2 AN and a target sum S. This is the input. So, we have a for loop for I in down to 1. So, what we are doing? So, for this for loop we are starting from AN. So, if AS is greater than AI, so for first point if AS is greater than if S is greater than AN, then we have to choose AN, otherwise because all the other, if you take the sum of all the other element from 1 to n minus 1, AN is greater than that. So, if our target is greater than AN, then there is no other way other than choosing AN into the knapsack. So, we have to choose AN. So, we take xi equal to 1, xi equal to 1 means xn equal to 1, that means we are putting AN into the knapsack and we decrease S by S minus ei. Else, so this is 3, 4, 5, else xi is 0. Okay. So this is the loop, and then finally, if s is 0, then we return this x1 x2 xn as a solution. Then we return x1 x2 as xn is the solution. Solution, else no solutions. Else there is no solution. No solution exists. Solution. Okay, so this is the algorithm to finding the knapsack when the ANs are in ANs are super increasing. So this is a what is the time complexity for this? This is basically a loop of size n. So this is the order of n algorithm. So this is a polynomial time algorithm on the size of the input. So this is good, but in general it is hard. Here we have a trapdoor. Trapdoor is this sequence is super increasing sequence. If this sequence is super increasing sequence, then we can, this problem is a easy problem. Otherwise, in general, this is a hard problem if we have not this information about this AIs, whether super increasing or not. So this is the knapsack problem. It is in general hard, but if our sequence is a super increasing sequence, then it is a easy problem. So we want to use this knapsack or subset sum problem to find out to have a crypto system, what is called knapsack crypto system, and which is developed by Markley Hellman. So let us talk about that crypto system. So this is a public key crypto system. So in public key, so Alice and Bob, suppose Alice wants to send a message to Bob. Okay, so what Alice, so now this setup Bob has to do, because Alice wants to send a message to Bob. So Alice has to get the public key of Bob. So that means Bob has to generate his public key private key pair, and Bob has to make his public key public. So this setup has to be done by Bob, because Bob has to receive the message. Okay, so what is this crypto system? So what we are doing, we are choosing a super increasing sequence A, which is A1, A2, AN. This is a super increasing sequence. Okay, and this Alice is sending to Bob. Bob is sending to Alice. Okay, so now plain text is a n bit number. So plain text is, so this is say x, or plain text is x1, x2, xn. It is a n bit number. So what Alice is doing as an encryption, so Alice is generating this S summation of xi ai 1 to n. This sum is the ciphertext, and Alice is sending this S to Bob. Okay, so now what Bob is doing, Bob is getting a S, and Bob is having this super increasing sequence. So Bob will apply the algorithm which we have just now discussed, that polynomial time algorithm, and Bob can get the x1, x2, xn. the message. Okay, so this is the decryption of Bob. We can take an example. Okay, suppose the super increasing sequence is say 171, 197, 459, 1191, 2410. Suppose this is the super increasing sequence we are using here. Okay, so now, so this is n is equal to 5. So now suppose now suppose Alice is choosing a secret. Alice is choosing this vector x, say 0 1, say 0 1 0 1 and 1. So this is the plain text. Alice is choosing this plain text. So what Alice is doing? Alice is encrypting using this with the super increasing sequence A, and Alice is getting the ciphertext S, summation of AI xi. So if we are doing this, just take this sum, and Alice is getting 3798. 3798 Alice is sending to Bob. Now what Bob will do? Bob has to apply the algorithm which we have discussed, that super increasing algorithm. So now, so in that loop is there, I is from n down to 1. So 3798 is greater than 2410. We are applying that algorithm which we have discussed. So then we have to add this, otherwise this is super increasing, otherwise by summing this all we will cannot able to cover this. So we have to add this. So that means x5 is, so x5 must be 1, and S is reduced to now S minus this 2410. So this is 3798 minus 2410. So this is basically 1388. Okay. Now again we compare this with this. Now this is greater than 1388 is greater than 1191. So that means x4 has to be 1, and then we deduct this s from 1191, and then we got, say we got this number, and slowly we will just continue this fashion, and we can see that x3 is 0, x2 is 1 and x1 is 0. Okay. So finally Alice got this x, plain text is Bob got 0 1 0 1 1. Okay. So now this can be achieved by Oscar also, because there is no, because this is the super increasing sequence and this is Alice, Bob is making public. So Oscar is also knowing this super increasing sequence A. So the same thing, same algorithm Oscar can also mount, and Oscar can get this X. So this crypto system is not secured. So this is called easy knapsack. Easy knapsack crypto system, and it is not secure because anybody can, any third party can mount this. Okay. So now the idea is how we can make it strong, how we can make it hard, because the super increasing property is, if we just make it public, then everybody, if everybody knows this, then it is a anybody can apply that algorithm and get the message. So now the challenge is how we can make it hard. So, the idea is to do the modular operation. So, let us go for this knapsack crypto system. This is called easy knapsack, which is not secure. Now, we will go to the original knapsack crypto system. Okay, so we have to somehow destroy this super increasing property. Okay, and then we make that sequence as public. But again, Bob has to get back that super increasing property in some way, so that Bob can apply that algorithm to get the message. So, that is the idea. So, idea is somehow we need to destroy the super increasing property before making this sequence public. Okay, so that is the idea. So, what we are doing? So, Alice wants to send a message to Bob. So, Bob has to generate his public key private key pair. So, this setup Bob is doing. Okay, so what Bob is doing? Bob first choosing a super increasing sequence. This is a super increasing sequence. And this is not public, this is secret. This is a secret key of Bob or private. This Bob is not making public. Okay. So, now what Bob is doing? Bob is choosing M and W such that M is greater than summation of ai prime I is equal to 1 to n, and W is basically chosen such that GCD of M and W is 1. So, that we will have a we will have this W inverse. W inverse I mean exist under mod M. So, that is the idea. So, okay. So, what we are doing here? So, we are just choosing this M and W such a way this, and then we denote this, we just multiply this, we create AIs which is basically W AI prime mod M. So, by taking GCD of M and W is 1, we will guarantee that W inverse exists under this. So, now this will destroy the super increasing property. So, this is the tactics. This way we destroy the super increasing property, and now this sequence we can make it public, this AIs. Okay. So, this AI is now public. So, this A is basically A1, A2, AN. So, this is no more super increasing. We have destroyed the super increasing nature of it by multiplying W mod M. So, this is the trick we are doing. So, now we can make this public. So, this is the public key of Bob, and this is Alice is getting this. Okay. Now, here the plain text space is basically n bit, and the ciphertext space is we have to choose mod M. So, it is number between 0 to m minus 1, n into m minus 1. Okay. And the key space is this A prime, which is the super increasing sequence, M, W and A. This is the key space, and among this this is the public. This is the public. So, this is doing by Bob, this setup is doing by Bob, and these all are private key of Bob. This Bob is not revealing. These are all secret to the Bob. Okay. So, now what is the encryption? Now, Alice is choosing a message M. So, Alice is choosing a message M, which is a n bit number, and then encryption is basically Alice is just doing this. So, this is the K is the public key of this is we can say A is the public key of Bob. Using the public key of Bob, Alice is just doing the summation of AI Ki, I is equal to 1 to n. Okay. So, this is the encryption and this is the this is our S, and this is the ciphertext Alice is sending to Bob. Now, how Bob will, so this is encryption, this is this is encryption. Now, at the decryption, what Bob will do? So, at the decryption what Bob will do? So, Bob is getting S, which is nothing but summation of xi ai. Okay. So, now Bob will apply W inverse on both sides, and W inverse will exist because we have taken GCD of M and W is 1. So, that will guarantee that W inverse will exist under mod M. So, Bob will compute this mod M, and this is say S prime. Okay. Now, this is basically what is S prime. So, S prime is basically, so W inverse, what was S? S is basically, so summation of A1 x1 plus A2 x2 plus An xn. So, now this is W inverse A1 x1 plus W inverse A2 x2 dot plus W inverse An xn. Now, this is nothing but, so AI are basically AIs we get from that super increasing sequence by multiplying W AI prime mod M. So, if you multiply by the W inverse with this, so it will give us just the AI mod M. So, this is basically AI prime, so A1 prime x1 plus A2 prime x2 dot An prime xn. So, this is a, now we can, now Bob can apply that algorithm, polynomial time algorithm, and can get, because this, now this sequence is super increasing sequence. So, now Bob will apply that polynomial time algorithm and we will get back this xi's x1 x2 xn. So, this is the plain text. So, this is the decryption process. So, Bob has to apply that polynomial time algorithm, but now this is super increasing sequence. So, this is the knapsack crypto system where we are choosing, Bob is choosing originally super increasing sequence, but Bob is destroying the super increasing property, and again Bob is at the decryption phase, or Bob is getting back that property and doing this. Okay. Now, let us take some example, quick example. Okay. So, suppose, so this is Bob has to do, because Alice wants to send a message to Bob. So, this setup has to done by Bob. So, Bob is choosing a super increasing sequence A prime, say 2, 5, 9, 21, 47 by 45, this 2, 1, 5, 4, 5, 0, 9, 4, 6. So, one can easily verify this is a super increasing sequence. So, this is Bob is doing, because this setup, because Bob has to get the message. So, this setup is done by Bob. So, this is one of the Bob public key. So, this Bob is choosing a super increasing sequence, this is a private key of Bob, and Bob is keeping this as a secret key of Bob. And then Bob is choosing M and W, and one can verify that GCD of M and W is 1. So, that will guarantee that W inverse will exist under mod M. Okay. Then we can multiply this, these are the AIs, so AI prime. So we can just compute W AI prime mod M. So if you do that, then we get the A vector as 575 436 1586 1030 1921 569 721 comma 1183 5740. So this is the public key of Bob, and this Bob makes this public. This is no more super increasing. We destroy the super increasing property, and this is basically EB, public key of Bob, and this is sending to Alice, or Alice has to get it from the public key directory. Now suppose Alice choose some message X, say 1011001111. Okay, now Alice is having this public key of Bob, which is no more super increasing. So Alice will compute summation of XI and this is basically 6665. Now this is the ciphertext Alice is sending to Bob. And now for Oscar is knowing this, which is not super increasing. Oscar is knowing this sum. So for Oscar it is a hard problem, because subsystem problem is hard in general. Now decryption is just we have seen. So Bob can just apply this W inverse S mod M. So this is 317 into 6665 mod M. So this will give us 1643. So now we know this is basically summation of Xi AI prime, which is this sequence is super increasing. Now Bob can apply that algorithm which you have seen, the polynomial time algorithm, and Bob can get the plain text 1011001110. So this is the decryption. So this is the knapsack cryptosystem. Thank you.